Hi, my name is Dale Maley. Today we're going to talk about a very interesting recent project I did. A little background on this project. I first designed and built this model back in October of 2018. And that's been 6 years ago. But I do remember I tried to use a free software program called Linkage.Exe to help design the model. But I could never get that software to run right. So I went back to SketchUp, a free drafting program, did some trial and error design, and built the model. So in December of 2024, I hadn't run this model for a while, so I retrieved it, and then I wanted to film it to put it into a new YouTube video where I show more than my 40 hand-cranked wood models in action, and this is one of the 40. However, when I went to crank it to make the video, I was really surprised. The red piston had very little travel. I measured it and it was only 1 9/16 of an inch. And I would have much preferred having a piston travel up in the 3 or 4 inch area just to make the model more interesting. So I decided to revisit the design of this model and see if I could optimize it to get some more red piston travel. So I decided to try that free program again. It's actually, the author is David Rector, and it's called Linkage.Exe. So I thought, I'm going to want to try that program again. So I did go and see if there was a more recent version from 6 years ago, and there was. So I downloaded the new version, which was a different version I had 4 years ago. Now the latest version that I downloaded was 3.16.42 as of December 7th, 2024. And here's the web address of where you can get a copy of his free simulation software. So any new piece of software that you use always has a learning curve associated with it. It takes a while before you figure it out and become proficient. I messed around with this program some more, but I found it really difficult to try to draw my mechanism in that program. However, I am very proficient at the free drafting program called SketchUp. Probably spent over 1,000 hours on it. So for me, the easiest process to model these different designs was to design the linkage version that I wanted in the SketchUp program. Then in SketchUp, I can easily dimension the X and Y coordinates for each key point in the mechanism. And I printed that out from SketchUp. Then I went into the linkage program and I just entered the X and Y coordinates. That actually worked very well. So let's look and see how I designed this linkage in the SketchUp program. So here's an actual image from SketchUp. And this is a simple version of this mechanism. And you can see the triangle over there. That's the moving slider on there. So anyway, I went in there and designed it, and then I could go in and dimension it. And what I want to end up with is the X and Y coordinates for each key point. And once I have those, I can enter those into that linkage program. So once you have the X and Y coordinates for each key point, you go into the linkage program, and you can see my mechanism drawn here. And what I do is go pick each point one at a time, and I picked one here. You can see the red arrow there. You go to the top of the program and you change the X and Y coordinates to what you want. Once you've done that point, you move on and do the rest. Once you've got the design updated to the latest version you want to test, you can run the model and then measure the resultant piston travel. So now we'll watch the linkage model actually run, as shown here. And you can see the slider bar, it slightly tips as it goes, but it moves back and forth. Then what you can do is go in and actually measure how much the piston travel was and record that for that design option. The next thing I wanted to do, what in engineering terms is called a sensitivity study. So in this model, there's only 3 key inputs here, and those are how long are the crank arms, and what's the angle of the crank arms to each other, and what's the length of the connecting rods. Now in my model, the crank arms are the same length and the connecting rods are the same length. The only output here is the piston travel. Once you do this exercise and you vary the inputs, you get a sense of how to optimize the model by doing this study. Now we need to define the different terms that we're going to use when we do our sensitivity study. So what I've done is show those on a drawing or sketch of this mechanism. So you can see the length of the crank arms, the length of the connecting rods, the slider moving back and forth, etc. Now, one design option on the crank arms is just to have them opposite each other, so the angle in between would be 180 degrees. Or you can choose to have them offset to each other. But we kind of need to define which way are being offset. So in the left-hand version, which is case number 6 in our study, that angle goes over to the left. On the other case over there, case 7 on the right, the angle is actually pointing towards the moving slider. So in this sensitivity study, I ended up looking at 8 different cases. And I took the baseline case, which is 1. Then I said, well, what if the cranks are a little bit longer, or if they're a little bit shorter, what does that do to piston travel? And then I said, what about the connecting rods? What if they're a little bit longer, a little bit shorter? What do they do to piston travel? And then if you vary that angle between the 2 crankshafts, what does that do to piston travel? So you can see on the far right, the piston travel, the smallest I had was 1.38 inches, and the largest I got was just over 5 inches, 5.23 inches. So by changing these parameters, you can really change the amount of piston travel quite a bit. So the sensitivity study showed us that if you increase the crank lengths, that will increase piston travel. You can only increase the crank so much until the point the model won't run. If you have longer connector lengths, that will decrease your piston travel. And if the angle between the cranks is away from the piston, as we just looked at, the piston travel goes down. But if the angle between the cranks is towards the pistons, the piston travel goes up. So I ended up selecting case number 8 to improve the piston travel on my physical model. I changed the crank angle, made 2 new connector rods, and my travel increased clear up to 4 3/4 inches. Now here's a video of my original baseline model. And as you can see, the red piston barely moves. It's only moving just a little over 1.5 inches. I wanted to have much more, like 3 or 4 inches of travel. Now here's a video showing how I dramatically increased the travel up to 4 3/4 inches by just making a couple changes to the physical model. In this video you can see the complete model in action after I made the changes, and I got the increased red piston stroke that I really wanted. So some closing thoughts on this project. This particular model is very difficult to optimize without using some type of simulation software like this linkage program. If you don't do that, then you're going to have to try to do trial and error using SketchUp drafting program, or you could make up a mock model and then use some thin Luan plywood links and try to do it that way, trial and error. Now the methodology I used, where I got the X and Y coordinates from SketchUp and then I input those into the linkage software, really worked the best for me. I may use this linkage software to make some other new hand crank models. So in summary, this short video explains how I optimize a rather complex hand cranked model. Hopefully this video gives you some ideas and helps you on your projects. I hope you enjoyed the video, and please subscribe. Thank you.